Welcome everybody to the Distinguished Wireless Seminar today. My name is Ashu Sabarwal. I am the department chair in Department of Electrical and Computer Engineering at Rice University. Today, it's a great pleasure to have Professor Kaushik Chowdhury, who is a professor and faculty fellow in the ECE department and also the associate director at the Institute for the Wireless IoT at Northeastern University in Boston. Kaushik is very accomplished researcher, has won many awards. I'll start by listing a few of them. A Presidential Early Career Award in 2017, DARPA Young Faculty Award in 2017, Office of Naval Research Early Career Award in 2016, the NSF Career in 2015. He's also won several Best Paper Awards in many conferences, including Infocom, Globecom, 3 at ICC, Census, ICNC, and DICEPAN. In addition to all these roles, he is also the co-director of the Platforms for Advanced Wireless Research Project Office and the Coliseum RF Emulator. And he has very wide research interests spanning applied machine learning for wireless systems, network robotics, wireless charging, and at-scale experimentation for emerging 5G networks and beyond. So we are very happy to have Kaushik here. Before we start, and I hand it to folks, just as a reminder, if you feel free to put your questions in the Q&A box, and we will ask most of these questions in the end. But if there is some burning question you would like to ask in the middle, feel free to let us know, and we can interrupt and ask Kaushik about those questions. All right, with that, Kaushik, it's all yours.
Thank you. Thank you very much, Ashu, and thanks for everyone for inviting me to this distinguished seminar series. I'm extremely happy and pleased, and I'm just going to. So thank you for the invite again. So today's talk is going to be by public demand, I hear, on UAVs, and the title is Airspace is the Final Frontier. And I'm going to tell you a little bit about what we've been doing with communications and some aspects of sensing, and how this all comes together in a fascinating vision where UAVs are all around. So we're going to start with just an introduction, and I'm going to tell you a little bit more about the specific works that I'm doing. So very pleased to be working with some outstanding men and women here in my group. And this particular work that I'm going to be presenting today is mainly by these individuals whom I have marked out in these blue boxes. So they are really the people who are doing the work. And I think I have the easy role here to just present. So to move ahead, I'll be covering a couple of topics, and I'll try to be brief in a way that we can cover good ground. The first one is, how do we have millimeter wave radio mounted UAVs? How do we do aerial beamforming with UAVs? How do we recover from jamming attacks? And a few other topics. I'm just going to give you a glimpse of some other works that are a little bit more interdisciplinary that combine UAVs with some aspects of charging, deploying, etc. Okay, so here's my start, right? We've been fascinated with flying machines, and this goes back. Our fascination goes back centuries. So as you can see from these little pictures out here, and more recently, if you recognize that little carrier that you see, that was used by the Avengers. So if it is cool for, I don't know, Captain America and Iron Man, it's definitely cool for me. So this is a fascinating area, and one of the reasons from a more economic standpoint is that there's a big market for surveillance and monitoring. There's also a big market for rural broadband, and perhaps it can be the only way one solves the problem of deploying infrastructure without installing towers in the middle of nowhere. So aside of rural broadband, there is a great demand for flexible 5G deployment, where you can imagine that complex infrastructure costs and fiber layers would not be required. So this is another vision that we feel that could be revolutionized by these base stations mounted on UAVs. So with that, let's dive down into the first topic of the day. And so I'm going to talk to you a little bit about channel modeling work that we have done at 60 gigahertz. And then I've listed a couple of references from which some of this work is taken from. So this group here, the attendee group here, is of course has plenty of works and expertise in the millimeter wave band. So I'm not going to extol the virtues of why we need the band, but just I want to make one comment here. So if you look at just one piece of the spectrum that's available in the millimeter wave band, if you just look at the 57 to 71 gigahertz, and within that, a part of it is already for unlicensed use. You have more spectrum here than all the sub 6 gigahertz bands combined. So here's a massive opportunity that you really want to exploit. Now, when you want to do this, there are challenges. And the challenges are that you have to combat environmental effects. You have to overcome high attenuation. You need directional beams, and sometimes you need also complex phased arrays, and the size of this can become a problem. And being able to deploy them in some of these aerial systems can become a problem. So I will talk about this some of these challenges in context of UAVs in just a bit. So I just want to point out to some important related work, and so there's a vast literature on all of these topics, and the papers do cite all of them. But I just want to single out a couple of these works that I feel are important. The first work is the work by Walid Saad's group on analytical channel models for millimeter wave UAVs. Now, this work is important because it provides a closed form approximation. But however, it does assume that the hovering follows some set of Gaussian distribution, and it takes some of the data from prior works. So there's no experimental validation in this work, but the model does have a closed form representation. And I'll show you how does this perform with the work that we're doing. Other work, so the papers we cite here, and some of the authors may be in the audience today. So I just want to point out to this one paper that makes it very clear and says that if you are in a bad location, then no matter what digital beamforming you do is not going to work. So you really need to do something else beyond just call beam searching again. So what can we do as a result, right? So as a result, if there are obstacles and there's an obstacle between the UAV link, how can we overcome that obstacle? And so one of the papers here, they say that, hey, you can do these backhauls by having a secondary relay UAV and offload some of the links to them. So you can sort of reroute around the obstacle. So you have to have another UAV that is on the side. But in many cases, you may not have that flexibility. So I just want to say that important work, but it does require some additional infrastructure support to make that happen. All right. So let me start to talk to you about what kind of channel model are we building, and what are also the limitations of that channel model. So the first thing here is to note that we are using COTS equipment. So we are not designing our own phased arrays in a sense. So what you see here is an M600 UAV that is flying on the top, and there is a stationary ground-based receiver which is at on the tarmac. So if you observe a little bit closer, you find that this UAV is carrying what is known as the Teragraph Radio. Now, the Teragraph program is from the Telecom Infrastructure Project Office. It's from an offshoot of Facebook. And then they provide a very interesting system that works at 60 gigahertz, mainly used for channel sounding in these experiments. But basically, it has a 36 into 8 element array, and you can move this in the azimuth from minus 45 to 45 degree angle. So you can sweep the azimuth. But unfortunately, all the 8 elements of the column are wired to the same phase shifter. So that means you can't, with these radios, also form or at least shift in the elevation. So you're limited in one dimension only. However, this is still interesting, and you can do some great work with it. So what we are trying to do right now is we are trying to first model the air to ground channel. Now, this air to ground channel is going to be a mix of fading, which is in this case more large scale fading, and you can approximate that using the losses that you will incur from the free space path loss plus airframe related losses. That's what the second term is, airframe. But these are still deterministic. Now, we are not saying that we'll come up with our own free space loss model. There is a great work by Ted Rappaport who has a very nice model called as it's for millimeter wave rural and macro cells. You can apply that straight away. What we are trying to do is to bring in some of the more variable parameters of the radio, of the UAV, and fold these into a more realistic channel model. So as a consequence, we're also going to add a term which is sort of a little bit more on a smaller time scale, and that is related to hovering. So the end product of this, and I want to make it clear, will not be a closed form equation. It'll be a process through which, given certain parameters of the UAV, given certain parameters of the beamforming apparatus that you're using, you'll be able to predict a total path loss. So just to give you a sense of what this airframe loss is, so here is an RF anechoic chamber. It's a fairly large, it's an auditorium-sized RF anechoic chamber that we have at Northeastern. And so we fly our indoor drones there when the weather is bad, which is for most of the year. But this one is completely RF shielded. So we took these Teragraph radios, and we modeled what is the ideal radiation pattern. And so the ideal radiation pattern you can model because you know the antenna elements, you know exactly how they are spaced, so we can come up with this radiation pattern. And that pattern that you see is the small dotted line in this figure. Now, what if I take these Teragraph radios and I mount them on tripods and I place them at some distance away? And then what you see, and this is the electric field versus the azimuth angle of steering, you see a static radiation pattern, okay, which is sort of closely mirroring the ideal radiation pattern, but has a little bit more variability and fluctuation, and that is shown by the broken line, which is in this plot. Now, everything goes south as soon as you mount them on a real UAV and you start the propellers. And when you start to do that, you find that you have a 9.5 dB additional loss, which you did not see, you did not account for when you even performed the static pattern with the real radios. So the airframe is going to cause some losses, and we have to take this into account. Now, the last piece is the hovering piece, right? Now, the hovering piece is directly, it's a consequence of these the GPS satellites from which, and you have the GPS antennas on board, and you're constantly making positional corrections based on the signals that you're getting from them. And you'll likely see that there is going to be a significant deviation depending on what kind of GPS you use. So if you're using something like the stock GPS that comes with it, and that's what the plot shows with the slightly grayed color markings, you're going to have a lateral displacement of anywhere from about 0.5 meters to about a meter in any one direction. If you swap this out with an RTK GPS system, it's called as a real-time kinematic GPS, where you have a ground-based station which is looking at the same GPS signals and issuing a correction factor to the GPS module on board the UAV, you can bring this down to a couple of centimeters. So this deviation, this hovering you're going to see is going to be limited. So we're going to look at both what happens when you have GPS, when you have RTK GPS, and what is the effect of this. And just to give you a quantifiable visual as to what it means to have something hovering, as you can see on the right-hand side, you see an M100 UAV sort of hovering wildly because it does not have the RTK GPS. So this is the problem that is going to cause an issue when we try to train our beams, when we try to find the best beam. And this is what you want to avoid. So as I go forward, I'm going to keep some of the mathematics to a minimum here. But since this is a channel modeling talk, I do have to point out a couple of equations. So I'm just going to, at a high level, explain the intuition that goes behind designing these equations. So the first thing is that I need to move away from a Cartesian system to a polar coordinate system. And for reasons that will become clear very soon. So by this, what I mean is that I must be able to model or sort of map any hovering variation in the azimuth plane that is shown by the theta variable. So I'm moving my left to right, right? So that is my azimuth plane Also have an elevation plane that's sort of moving from the horizontal to the vertical direction. And then there's a radial direction in which sort of is moving closer and going away from you. So I want to map all these coordinates into this plane. Now, the problem here is a little bit complex. So let's just consider only the theta angle, okay? So only moving in the XY plane here. So here, assume that this is the UAV that is sort of facing along this line, right? Now, the UAV can have a yaw. By yaw, I mean that if I look straight at you and if I then start to look on the right, I have done a yaw. So this movement is can also be additively or can be added to a translational direction, a translational Y movement along with the yaw. So you have two of these simultaneously occurring events that must then be mapped onto the theta axis. So long story short, all we're trying to do is that we are trying to create, or what we have done in the paper is that we have developed, we have designed analytical expressions for the distribution along the translational movement as well as the yaw, and then projected them onto the theta axis. So when we do this and you normalize this over all possible variations of theta, what you get is a probability distribution of the UAV or sort of at what angle is it moving, and you can get a distribution of that using these techniques. So again, the paper goes into a little bit more details as to how you extract them from analytically from expressions. So now here is the two things that we want to do. Imagine that you have a static location. So you have a perfect beam alignment between, and these beams are all centered. Now the hovering is going to shift you around. It's going to go left and right. And because of this, you're going to have what you see on the left is what I call as misalignment loss. This means that you have the beams centered, but then the UAV is moving left and right. And because of this, there is going to be a different level of beam alignment that is going to cause the loss. So this is, so when I refer to misalignment loss, I just mean the UAV is moving left and right after it was centered at the optimal beam. Now there is another kind of loss, and this other kind of loss is what I call as the suboptimal loss because of suboptimal beams. And this is understood in this way, where imagine that you formed a beam when the UAV was hovering and it was already at a far end, and the beam was finalized at that point. But the UAV is not going to stay there for long. It's going to come back to its center position. So immediately after you form the beam, UAV started moving, and because of this, there is a defined loss between what could have been the best beam and what actually is chosen as because of this movement. So you can characterize this loss well. You can characterize this loss based on the characteristics of the beam. That is, how wide it is, how wide is your sweep, and this distribution, this distribution on theta that we just derived a few minutes back, where we were trying to say with what probability can a UAV be at that theta angle. So this, what this expression tells you is that I can find the probability that a certain beam U and a certain beam V were selected at the end of the beam searching phase, and this can be analytically derived as a function of the beam parameters as well as the distribution of position. Now, when you do this, when you find this probability of a certain beam being selected, we can find the loss because of these suboptimal beams. These so chosen suboptimal beams, this then becomes a deterministic function. Because if I know what were the best and then what you chose, I can find from the radiation pattern exactly what that loss is because of the suboptimal selection. All right. So with that, let's just see what is the effect of all of this, right? So if I start to plot just a static case, that means I'm going to simply have these two sounders facing each other without any airframe, without any propellers on. So I have a certain path loss, right? Purely based on distance. Then I bring in the airframe, and that's where you see that blue band coming out, which is adding to the path loss. Now, along with that, if I use an RTK GPS, that means I have very little hovering. What you see here is that any changes beyond the airframe are mostly sort of contained. You don't see a massive jump. If I remove the article GPS instead, and if I bring in a classic GPS, you see the blue line on the top, and that's where you have the combination of both the suboptimal beam and the misalignment. Remember, suboptimal is when you chose a beam where you are not, or not the best possible beam. You chose it when the UAV was far off, and you selected that beam, and there's a loss associated with that. And the misalignment is that when you chose the best beam directly aligned with you, and then you're moving left and right after you made the straight line or the best beam selection. All right, so let's move further and just put all this a little bit together. So I want to find the total loss. And the question you will ask is, what is the probability of a total link loss lower than, say, let's say 120 dB, right? So that's a question you want to ask this system. So just to drive a little this discussion a little bit further, let's take first out of this whole complexity the ones that are deterministic. So the free space path loss and the airframe loss, we can calculate them, we can pre-measure them, and we can estimate them very nicely. So let's take them out. You can obtain them from the deployment parameters and the known radiation pattern. Now comes the next part, which is the hovering statistics and the other beamforming parameters. And these will now influence what were the candidate beams that you could actually select for this. So you have a set of candidate beams that are actually feasible because of the beamforming parameters and the hovering statistics. Now from here, you find the suboptimal beam selection loss, as we found in a couple of slides ago. And this, as I said, given a choice of beams, given V, this suboptimal loss is deterministic. So you know exactly what is its contribution. Now the stochastic part comes in when you have the misalignment loss and a radial loss. That means the UAV is not hovering left and right above its center point, and then there's a radial loss which is going back and forth beyond, away and closer to you. So these are the two ones that are stochastic, right? And to do this, if you now start to look at what is a total loss probability given U and V, is really the only stochastic pieces here are the radial loss and the misalignment loss. So this becomes a function of these two, the probabilities of these two expressions. And what we do in this paper is that we integrate these PDFs over all possible options of the displacement as well as of the radial displacement to obtain the final loss. And again, we describe these steps, and just to show you whether or not this model works. Now focus your attention here on, so this is a CDF versus a path loss expression. So focus your attention on the experimental spine that you see that is sort of going on the right-hand side. Now you want your model to predict that experimental performance as well as possible. So if you just go with free space path loss, or if you go with misalignment loss with an ideal beam pattern, and this is what happens when you go with some of the related work papers. This is the model that you see. You're still far away. You can add an aerial beam pattern. That means you can start to integrate some of the airframe losses and the other hovering related losses, and you start to go closer. But if you use our model, which is it sort of draws in parameters which are very specific to that UV and to that particular beam transmitter, you have a nice mix, a nice match of the proposed model and the experimental. So what you're trading off here is that you're trading off accuracy. That means you can be almost like 0.2% to the experimental. What you're trading off is that you no longer have a closed form equation that you can just apply to. So this is a trade-off that you're going to make, and there are valid reasons to go with one or the other. So one of the quick fixes that you can do here is, now look, you were finding these beam pairs continuously as you're doing the beam search, but you're also at a certain location in space where you found these beams. So depending upon how often you're supposed to be in a certain location, you weight your beam pair, or at least the fitness value of the beam pair that you get. You weight it based on how far is the UAV from the point where it is maximally going to stay during hovering. And if you weight that, then you simply multiply the probability with which the UAV is going to stay at a certain location with what is the path loss you're experiencing because you chose those beams at that location. And when you do that, you find that already the standard gives about, in this experimental use case, about an 84 dB path loss, while the proposed is able to give us a much better strength. So what you see here is by simply weighting the beams uh, during the beam searching phase based on the displacement of the UAV, you are able to significantly improve performance. Now, just to take this a little bit further in this discussion, there are ways in which you can improve a link which is suffering because of various causes of degradation. So because of this hovering, if you have a very narrow beam width, the UAV may simply go out of the beam width range. So can you increase the beam width? Now, if you're out of range, that means, let's say that you are trying to, you've moved a little bit farther away, and if you would only rotate the UAV just a little bit, those two beams would overlap, and you'd be able to recover from the loss of or the path loss. So when do you rotate? And when do you know that there's an obstacle and I really have to move away? I need to displace both the transmitter receivers farther off. So I'm going to explain to you a couple of steps that we would take. And again, this is a process and a method by which you would eliminate one by one, and you would try to take the best action. So the quickest way to do this is to simply increase beam width. Imagine if you saw your path loss becoming higher than you expect, you simply you try to increase the beam width. And so here is a plot that shows you for different distances between transmitter and receiver. So each line that you see is one distance between transmitter and receiver. And each point on the x-axis is really your beam width, and such that, and the y-axis is the probability that because you chose this beam width, you are likely going to have an outage. So if you choose it carefully, if you given your distance and given your beam your beam pattern, you can set your beam widths in such a way that you can have a high percentage of beam alignment, given again the distance between transmitter and receiver. So you can try this first. So let's say you try this, right? And you find that even then you are still experiencing loss, or the path loss is lower than required. So what we did here was that we built a data set of these UAVs flying in different conditions. And as you can see, they are flying in an open parking lot. They are flying in a bushy creep probe area. And so what we're trying to do here is, can we find out whether there is a line of sight condition or whether there is blockage condition? So what you see on the top right is the theoretical estimated path loss, assuming you know the beam pattern. And since this is not uniform in all directions, so you have the transmitter beam index here and the receiver beam index on the y-axis, and it shows you basically the path loss. So you don't see a very symmetrical arrangement of these colors, just because we are taking an actual radiation pattern in building this. But this is still, in a sense, theoretical, because we are simply saying that what happens if this ideal or if this known beam pattern and everything else being static will intersect between the transmitter and the receiver beams. But when you start to do real experiments, you see that the experimental path loss and that's the one that you see at the bottom here. You see that it doesn't resemble this exactly. So there is still some dispersion that's happening. But if there is an experimental blockage, then this shape is something that is significantly different from this ideal loss. So can we train a network to identify these differences and say that, hey, this is a blockage condition and this is probably just normal path loss? So we actually did this, and we didn't train a deep neural network here, but we simply look at a normalized cross correlation of what you observe with the theoretical estimated path loss. So the top right-hand figure is then cross-correlated with any observed matrix. And surprisingly, you find that with a very high degree of confidence, you can say that if you observe a certain a normalized cross correlation, you can say that this point will likely lie on, in this example, it likely lies on the shape that resembles the blockage curve. So fine. So you say this is likely. So you can say that there is no path loss. Sorry, there is no line of sight, but there is still some things yet to be determined. Now, for example, can you fix this using an angular turn? So the first thing we want to do here is that we want to find out that what is the probability that your out of range is because of a certain choice of your beam sweeping range. So let's say that you have 15 or 20 degrees of beam sweeping range. Each of these values is associated that that there is a certain probability of outage, simply because if you would rotate a little bit more, then you would be able to recover. So we actually derived an analytical expression of this, and we find that we have a very good match with the experimental, and this is a product of I think 100 Monte Carlo simulations, and we're taking the average of them, and we're trying to come up with what is the one that you will use to, and if it does match the experimental one. So we say that, look, if for a certain beam sweeping range, you know what is the probability of being out of range. So if this probability is very small, okay, then you know that this is likely not going to be fixed by turning. You have to displace yourself and move, both the transmitter receiver moves in synchronization. But if this is quite high, that means it's likely because of your beam sweeping range, then you'd likely want to see how much you want to turn. So to measure this turning, what we do is, so think of this plot, this again, this beam, the transmitter receiver beam path loss plot. So think of this as a sort of an image, and each associated value of the path loss is indicating of a certain density of the pixels of this image. So you can actually use sort of a gradient analysis to see how much should you move from your center point right now to a better point, which is shown by the arrow on the right, which has lower path loss. And to do this, we are simply going to calculate the gradient at each point, and we're going to project this on the azimuth rotational axis. So not just that, that's just one gradient. We're going to average all these gradients possible. So just to give you a sense as to what is happening here. So I'm just going to give you a visual sense of what do I mean by this. So let's say you find the average gradient. And so these blue lines are a visual representation of what these gradients are. So here you can clearly see it is saying that there is going to be a net gradient, which is moving from your left to right direction. And there is going to be no gradient, or roughly infinitesimal gradient, that is moving from bottom to up. That means it's saying that the transmitter beam should turn by a certain angle from left to right, while the receiver beam should stay as is. And this is another example here where the gradients actually cancel each other out. So the average gradient is sort of zero, or it's very close to zero. So you're not crossing a certain threshold. In this case, no one needs to rotate. So here are some examples where a process by which you can use this channel model to come up with better beamforming approaches. So just to summarize the main contributions, so we are able to capture realistic effects of hovering and airframe and other beamforming parameters. And we can also do resilient beamforming by trying to detect what might have happened that caused a lower, that lowered the path. So, okay. So on the next piece.
Kaushik, before we move on, just a quick question, which maybe others are also curious about. Considering that drones will be flying a little bit at an altitude, there is a role of elevation here. And, yes. And then that role of elevation likely shows in the way your beams point. That means they have to point in 2D space, not in a 2D, in 3D right. space, not in 2D plane. Right. Could you comment on that?
Right. So what we did was this. So for the purpose of modeling, we took real measurements along the theta, but we said that the same pattern will occur along the phi axis. So the hardware constraint doesn't allow us to take the real measurements along the phi axis, sort of moving along the elevation plane, because they're all wired to the same phase shifter. but the formulation is independent um, of this 3D beamforming. I mean, the system doesn't allow; it just allows a single vertical beam in a sense along the vertical plane. But the formulation is independent of that.
Great. Okay, thank you.
Great. So great. So the next one I'm going to talk to you about distributed aerial beamforming, and here's the reason why we want to do this. So if you follow the FCC Part 107 rules, so I'm a stickler for rules, and my wife, who's an aerospace engineer, doesn't follow rules. So she always crashes the flight sim, and I fly away merrily. But if you're really serious about UAV flying, you have to go back and read the FCC Part 107 rules. And you cannot fly below 400 meters. You cannot fly over government buildings, over non-involved participants, human participants. So your receiver or your next hop may be somewhat farther away. And so one way to do this is if you want to do sort of a phased array like beamforming within the same transmitter, and this just shows you how you would adjust the phases of subsequent antennas of a linear array, just so that the wavefront arrives at exactly the same time. But in this example, what we want to do is something different. You want to show different transmitters doing sort of a coherent beamforming and getting the signal to the receiver at the same moment in time. So there are some interesting theoretical works, and again, in the interest of time, I'll just pick up the middle one here. The middle one actually is an interesting demonstration of this distributed beamforming. But what they do is the receiver sends back a 1-bit feedback. So the feedback simply says yes, no. Now it's up to the transmitters to search the space of, okay, let's try this, and let's try moving the phase back and forth, and it becomes a little bit complex when you have multiple transmitters available. So, to be honest, there aren't real demonstrations of distributed beamforming for UAVs, not to my knowledge. So we want to show that this is actually possible. So the first thing what we wanted to do was we wanted to try this out in a lab setting. So here are a number of there are these two transmitters, TX1 and TX2, and they are going to do beamforming towards this receiver. Now, the goal here is that you can see when both TX1 and TX2 are transmitting together, there is a substantial gain in the signal. And to just derive an insight as to what this gain is. And so I'm going to say here that if n are the number of transmitters, then you're going to, or the benefit here is to see an n-squared gain from the beamforming process. And so in this whole expression, if you focus on this equation on the right side, just focus on those two terms, the one that's inside the cost term and the one which is f. So your goal is to the term inside the cost term is really the relative phase difference. You want to make that 0 between the two transmitters, right? So then that cos 0 becomes 1, and that's maximized. And also your phase difference between any two transmitters the frequency offset between the receivers and any of the transmitters has to be 0. So that's why the f has to be constant. So you have to hold these two, you have to set the system in such a way that f is constant and that phase difference, that other blue term, becomes 0. Now, if you go a little bit further, if you extend this to n transmitters, and that's where you see that n-squared term comes in. You see those two summations on the right-hand side, and if that cost term becomes 1 at the end, then you get that n-squared gain, and that's where you'll be able to best utilize this system. So here is an urban downtown deployment. Imagine that it's a complex situation. You have UAVs moving in circles. There are some static hovering UAVs, and then there are other ground units that you want to beamform to. And there could be multiple of these, right? And they could be causing interference to each other. So in all of this, there's a question of how to do the beamforming, the signal processing aspect of it. And then there's an algorithmic aspect of it. So here's the problem here, that at certain locations, you are going to have, as you see on the left-hand side, you see there are structures around. You're not going to get a good clean signal. It's going to be a complex channel. On the right-hand side, on the top, you see an open blue sky, great beams, and you can really have so you really don't need a lot of these beamforming transmitters at that location, but in the first location, you might just need a couple more to overcome the back channel. So the approach to beamforming that we follow has two parts. One is the algorithmic part, which is how to prioritize which receiver should you send packets to, and which group of beamformers should be doing this. So that's an algorithmic part. I'm going to come to that part a little bit later on. But let's look at the process, the method in which we do the beamforming. So the method is that you generate or you create an OFDM packet, and you're going to take the beamforming weights that you receive from the receiver in the last iteration. You're going to modify your symbols with these beamforming weights. And you're also going to inject a gold sequence at the start of this frame. And I'll tell you why you need this. And then you're going to transmit this whole package together. Now, why do you need the gold sequence? You need a gold sequence which is uniquely generated for each transmitter. And this gold sequence is such that it has great correlation properties. That means if I take one gold sequence or one transmitter and correlate with another, I'm going to get an extremely low value and very high if I cross-correlate with myself. So, so for this, what I do is I take this gold sequence in two ways. One is I try to find out, so these are the cross-correlated values of the gold sequence at different instants of time from two different transmitters. You can see the value of this correlation, and you can see which transmitter is ahead than which other transmitter. And for in this example, the transmitter 2 should slow down by 20 microseconds so that the the transmitter 1 can catch up, and then they are simultaneously transmitting. And the other one is to really estimate the channel. So if you can extract an individual transmitter's gold sequence, you can simply find the H matrix and find the beamforming weights by inverting the matrix. So with this, so far we can do the beamforming, and then there's an algorithmic contribution to this. So just to give you a high-level view of this, so imagine that there are packets with different deadlines. So psi indicates a deadline of a packet. And you can have multiple packets for the same user. So for user M, I have P1, P2, and some other packets. So what I do is I order these packets by the deadline. So the highest priority packet is the one that must be transmitted ASAP. And so from these packets, from this ordered list of packets, I also find the rate. That means how many bits do I need to transmit? And I have a finite duration with which I want to transmit this. So from this, I obtain what should be the modulation scheme. From the modulation scheme, I map it to the SNR, that for this modulation scheme to work, this is the minimum SNR that I need, right? So from the SNR, now this becomes interesting here, that this is where I now start to map UAVs to a particular packet that will satisfy the SNR. That's where the beamforming comes in here. So imagine that I have these three packets, just for an example, and I have these UAVs that are trying to beamform to either N or M. So there are only two users. User N has one packet, user M has two. So as I start to add, so this is, I'm describing a recursive algorithm, which we go into considerable detail in the paper, but this is just to give you a one use case visual example. So I'm going to add packets. I'm going to add beamformers to that particular user and for that particular packet till I reach that SNR required for that particular user N. But every time I added a beamforming transmitter, I added an interference level to the next packet, the next priority packet, which was for user M. And so its required SNR just went up by these three notches that you see. So there is some margin here for user N, just because the last beamformer I added gave me some margin. But now when I start to look at my second user, it may happen that I'm also increasing my interference for the first user, and I need to budget for that. So in this example, as you'll soon see, because I needed to add more users for the second packet, I could not meet or I could not make a satisfiable assignment that also satisfies the higher priority packet for N. In this case, the algorithm rolls back and its recursive loop executes. It removes this packet and it goes to the next priority packet, and the system occurs all over again. So this is broadly the approach that we have taken to do the scheduling. And we compared this with just a capacity maximization approach, which is based on the Hungarian, and a slightly modified version of the Hungarian, in which, remember, we want to do multiple transmitters to one receiver. And the classic Hungarian is a bipartite matching graph. Once you allocate a left-hand side to a right-hand side, you can't have another. So we want to have multiple transmitters beamforming to one receiver. So for that, we modified by creating like dummy nodes of receivers and running this multiple times. It's with some added complexity as we show here. So just to give you a sense of where we implemented this, so for the real live demo of this, we implemented this on a B210, with a B210 mounted on a M100 UAV, and this shows you an experiment conducted inside our RF anechoic chamber with some of the cones removed. But what this shows you here is that we can support multiple different modulation schemes, going all the way up to 64 QAM. And so very soon now you will see that so pardon the type, but it should be frame error rate. So before the beamforming, you see a high frame error rate. After the beamforming starts, you find that almost all the modulation schemes can be supported. So this is actually working. If you go outdoors, you find that when you have a single transmitter, and if there's an interferer, you find that you have an extremely high frame error rate because of the corruption caused by the interferer. However, when a bunch of these other UAVs move towards this transmitter and start to beamform, you find that you are able to then continue this the reception without any appreciable loss. So one thing what we did was we could not explore a whole lot of these in the real world. So we went to the Colosseum, which is the world's largest RF emulator, and it's home right now at Northeastern. So it can emulate virtual worlds. And the way we do this is that we map each UAV to a certain user system. So we have 128 of them total. So we can map our UAV to one of them, or a ground unit to one of them. The only problem here is that they have to be time synchronized. So only quad 1 is time synchronized. So we are limited in terms of how many nodes we can execute for this beamforming approach. The RF emulation manager pulls out channel, we need a 4-tap channel matrix. So a 4-tap channel matrix is pulled out from memory, and it resembles, you can model this in, let's say, a different software and add this channel matrix for use live in the system. And in real time, these channels are combined with those active transmitters, and you estimate also the signal strength at the intended receiver and also the interference at any other receiver. So when you do this system and we evaluate what was the performance, you find that for this architecture that you saw, is interestingly that not all UAVs need to beamform it all the time. So this number of beamformers changes over time. And also, we see that if you do the beamforming, that is a proposed approach, the probability of frame error rate is significantly reduced compared to other alternate approaches. All right, so with that, just to summarize the contributions, so we did plenty of these works on how to synchronize, how to do the channel compensation, and then implemented this both live and in the Colosseum. So I don't think I'll have a lot of time to talk about the jamming part, but I just want to tell you a high-level view of why and what would be an interesting thing here. So our whole goal is this. We've always been inspired by the heavens, right? We look up at the sky when we want an answer. So what you see in the sky are constellations. So when you want to look at constellations, the goal here is that, can you create constellations by physical movement of the UAVs? And these constellations can represent bits. And you can communicate bits by the way the UAV is moving in this constellation space in the air. How would you detect this? You would detect this constellation through a millimeter wave sensor, which is sort of ground mounted. And you will see how the UAV is moving and establish the information that it is trying to convey to you. And why would you want to do this? Imagine that if you are jammed by a certain external interferer, and you have no way of communicating which band or which entire new spectrum you want to go to, you would simply slightly shift your locations and allow this relay without actually communicating live RF signals. So that's really the whole concept of this. And so we want to create these constellations, and this work really tells you how to create those constellations in space. So we did a lot of work with these millimeter wave sensors, where we tried to again characterize how well could we use the Texas Instruments sensor that you see here to identify and to pinpoint where the UAV is in space and find out the error bounds in which the hovering plus the sensor, how do they jointly contribute to the error? Now, when we do this, what we can do is we can really identify where the UAV is. And for that, we modified an existing algorithm called DP-scan. And the DP-scan uses a way to cluster these points together. These are points that you're obtaining from the millimeter wave sensor. Now, you want to know which of these is really the UAV. So we carefully designed these, and the whole goal here is to cluster them in such a way to first find suitable clusters, and then find a specific point in the cluster that the UAV is likely to is going to reside in. So we enhance this DB scan algorithm with other knowledge of UAV specific knowledge. And what is this knowledge? How many points should you consider? And what should be the radius at which you should look for points? And only those are considered as valid clusters. So we did a lot of experiments on this to identify what is the optimal number of points that will justify, which will create meaningful clusters, and then how do you find the exact point by looking at the histogram of how often are points clustered around within that same cluster. All right. So this was the whole goal, to create these constellations. And if you can create these constellations, and this is in a radial directions. And so I won't go into the mathematics of this work, but in the paper, we have derived specific values for, if you take let's say, I shouldn't call it as a QPSK, because the concept is it's not really QPSK, but a 4-point constellation. Then what is the probability of a symbol error that the UAV communicates down to the ground-based station? Similarly, for a 2-point constellation. So we have derived this in the paper for a bunch of these different constellations in space. And to do this, so I'll just skip this. The whole goal here is to come up with a metric that makes sense, because now you have to move physically before you can start a new channel. So just to give you a sense of whether this works or not. So we had to redo a lot of ROS programming modules to enable this. So how to create a constellation, how to do manual flight control, how to do navigation, and change some of the default ROS modules with some of custom written ones to enable this to happen. And so you actually see that this can overcome jamming, where if the jammer disables the reception in around point number 2, the UAV is able to communicate a whole new spectrum band and is able to then resume communication. So there are some theory and algorithm they have developed here. We have shown implementations here. And I just want to point out, my last slide is going to be on some other topics that could be of interest. Now, one problem is deploying UAVs. Now, we really don't think too much about where should the UAV be deployed and the time it takes for you to really deploy the UAV to that point of interest. So we came up with a method where the UAVs could ride a bus, and depending upon bus routes and their bus schedules, you will be able to say which UAV should hop on which bus. Crazy, right? I mean, they're supposed to fly, but you can deploy them effectively by choosing intelligent bus routes. And we did this for a live case of the city of Bologna. Charging UAVs. Now, this is a big interest area for me, where UAVs have to be autonomous. And one of the autonomy reasons and the ways to enable autonomy is to enable it to charge autonomously. So this is an early prototype of a system that we built that allows the UAV, that pins the UAV down and uses inductive charging to charge the UAV. And once this is done, you can see dashboards that show how much voltage and current that there is. And once you charge it, it is able to fly off. One of the next the works is, think of UAVs as edge computing boxes. Now, where would you deploy this edge computing that makes sense? So here was a combination of edge computing and a software-defined network that we built on these UAVs and showed that you can think of them as a computational resource. And when should you compute, when should you communicate data for this computation? And one of my last and one of my favorites here is applying deep learning to identify a specific UAV. So we can identify a specific M100 UAV from a fleet of M100 UAVs. We can identify a different make and model of a UAV by simply using deep learning on its RF signals. So with that, I'll stop here.
Fantastic talk. So there are already 2 questions by Mariam. So I've given her access to talk. And then Mariam, why don't you go ahead and ask your questions?
Okay, thank you for the great talk. My first question is, when you're performing the distributed beamforming, how are you changing the location of the drones, because it's placement and assigning the beam to the drone simultaneously? And is there a possibility that you move one drone very close to the receiver so that you don't have to do distributed beamforming anymore?
Yes. So what you say is right. In fact, if you look at, I think the Prezi will probably, let me see if it allows me to show you this. So if you look at this, we are not changing the location of the drone. We are saying that let the drone fly where it is. But we do have a loop where you are able to get the feedback from the receiver and adjust the beamforming weights on the fly. So that we have, yes. But we don't position the drone. So we will let the system figure out the best weights. Now, it's not always that you need beamforming. So if you look at this, there are these UAVs here that are doing beamforming to this one. There are a number of UAVs, so shown by TX. All the TX are UAVs. They are not doing beamforming. So they are just doing straight one-to-one. So, and this changes here again. So it's fine. It's okay to not do beamforming unless you have to do it.
Okay. And my second question is more of like a general question. And I think you talked about the charging at the end as well. But when you are placing the drones in urban settings, so what's the spatial extent of the region that one drone can cover? And how long can it fly before it needs to come back to a certain recharging station to get recharged?
Right. So you ask an interesting question. Now, how far it can cover is a function, of course. Both the questions are related to its battery.
Flight time constraints.
Right. But so here's the thing. I cannot give you an answer without you telling me first what is its payload. So here's my answer I'll give you some numbers for this. So if you take an M600 and if you don't load it up, right? So it can carry about 15 kgs of weight. If you load it fully to 15 kgs, from its default flight time of 30 minutes, you are down to about 10 or 15 minutes, 12 minutes mostly. Yeah. So, but this is just this drone, right? So it depends upon what drone and what load carrying weight. So that's something that we need to be very careful about when we design these future base stations and antenna systems. Ideally, if you could integrate them into the airframe itself, that would be a big weight saving. So swap C is a big deal. We haven't solved that problem yet.
Yeah. So I think it was more on the, so like you said, it's at most 30 minutes. So the ones that we are using the range is between 20 to 30 minutes. So you can cover maybe, a few kilometers of area. The drones can move, within that range and cover it.
Well, use the work that we did, make them ride a bus, make them land on a bus, have the charging pad on the bus, and let it charge as it moves from the bus from one point to the other, reaches a viewpoint and flies up. And so we came up with a theoretical formulation as to how you could do this for different viewpoints of a city. But if you spend all your energy going to a place, you're not going to spend anything else doing the real monitoring.
Yeah.
It's a tough question, yes.
That answers my question. Thank you.
Great, thank you. Edward, you're up next. Go ahead, please.
Thanks. I also have two questions if I don't get thrown off first, but also thanks for the talk. I mean, really, really interesting work. Let me ask first about the beam forming in the first part of the talk. That I mean, it seems like quite the challenge to maintain and align those beams. And if I understood most of the work, the experiments were hovering, and I'm curious about your thoughts about if the drones are moving, if we're trying to maintain high data rate beam formed while they're going 40 miles an hour and might be and moving in 3D, they could be, you know, going up or down as well. Are you optimistic that we can maintain high data rates in those scenarios?
Well, look, so high speed. So this is a broad question of high speed millimeter wave beamforming, which I think is a whole challenge in itself. Now, if you tell me that there is a deterministic approach, for example, if you tell me that this is a constant velocity of travel, one can anticipate for it, one can plan for it. The problem with these drones is that not only are they moving in that case in that speed, but they're also then moving around their required location. They're also hovering in a sense around the location where they're supposed to be. That creates this additional problem. Now, there are lots of works which actually try to anticipate where a node is going to be next and pre-plan and sort of preset the beam weights, and so there is a solution there for sure. But practically, look, I'm a systems person, so I like to sort of implement it live on a real device. And what I've seen is that even with the static hovering case, it's a pretty hard problem. While there are theory works, I'm skeptical if they will be able to translate as is into a real system.
Okay, thanks. Well, that's a good challenge then for all of us, all the students. Who's going to do the flying drone beam forming? Okay, I'll ask my second question then. The security problem and getting really that location based, almost like a covert channel. I thought that was really interesting idea. And have you thought about putting RFID on the drones and just make that entire process easier to communicate via the location? Have you thought about that?
So is the question on so if I understand this right, so would you be able to identify the location of a drone without doing the millimeter wave sensing part? Can you just put an RFID tag and then just sort of scan the tag and obtain the location?
Yeah.
So interestingly, so this Mobicom, we had this paper on distributed antennas, RFID reader systems. And we did this for an apparel store. So imagine you're going with a bag full of clothes and you just walk out, you don't stop. And these multiple antennas query the tags and establish a location for that. So it's certainly possible. My only problem here is that the way we architected this again was we had to put the readers in a virtually a 3D space around the drone, just because we could never be assured of a clean reflection back. So I'm wondering how would we put these readers perhaps on poles so that we have a good coverage of all the angles where the drone could be, because it's also doing its yaw, lift, pitch, roll, and so I think that's a great idea. We can locate that. We have done this for more mundane settings of commercial grocery and apparel shopping, but yeah, why not?
Okay. Thank you. Another challenge then. Appreciate it.
Sorry,
Fantastic. We'll continue. We have two more at least. Yasemin, do you want to ask next?
Sure. So thank you. It was a very interesting talk. My question is also about the beamforming you mentioned. So given the hovering issue and the need for 3D beamforming with UAVs, I was curious about the placement of millimeter wave antenna array on UAV. So I would imagine that with intelligent sort of placement, we can harness diversity, and maybe that can solve some of these hovering issues.
So the hovering is going to be there one way or the other. It's a problem that happens. Yes, it happens more if it is if you're in a GPS sort of, if a bad environment where the GPS signals have multipath. But so the GPS, so the hovering is going to be there anyways, right? So now I think the other thing is, can you overcome this using maybe a number of these millimeter wave antennas? Or so when you say harnessing diversity, I'm trying to understand. So you will use the motion itself to have additional copies of the signal at different sort of transmit points, and thereby gain the diversity, right? Yes. So in the channel modeling experiment, we were not looking to see what would be the effective bit rate at the end, though that's certainly, I think, the end goal of any channel model. We were mainly looking at what would be just the path loss. But I think you have a point here that why not convert the hovering into something that you can use? So there was a work,
exactly, I guess.
Yeah.
I think my exactly, you got the point. So basically, using harnessing hovering for communication or for security issues. Yeah.
Well, let's just write the next paper together then.
Yes.
Excellent.
But,
Excellent. Already a successful talk. Several papers have come out here, and then we have Jai.
Hello. Really great talk. Thank you. So my question is also related to the security, and then originally I wasn't like super clear about like the threat model, but from the earlier discussion, you and Dr. Nagli, I think now it's more clear that I mean, like there are still like some parts I'm not so sure like what exactly is the threat model, and then is your goal try to identify the drone location despite interference going on?
Right. So I'll give you a very concrete use case. So the M600 that we used here for these experiments. That, by the way, that's me carrying the M600. It weighs a ton, by the way. It's so this M600 that we used is used by the U.S. Joint Forces for a hunter-killer application. So this M600 goes and actually literally throws a net on an adversarial UAV. This same M600 was used by bad actors to assassinate the Venezuelan president 2 years ago. So the same model, the same make, is used by blue team and red team forces. Now, if you see them coming up front, would you be able to identify this that this is a UAV that that is your blue team UAV, and more so, can you identify that this one is truly an adversarial UAV if it is broadcasting an ID that is associated with a known blue team? So that is the challenge. And the DoD is very concerned that with the advent of these software-defined techniques, you will be able to impersonate another UAV. And what we propose to do is to use our deep learning RF fingerprinting pipeline to identify an individual UAV of the same make and model, and just a different unit of the same make and model, as well as a different UAV type itself, and thereby just give you a full classification as whether this is something that belongs to you or is of a malicious nature. So that was the goal of that fingerprinting work.
Excellent. And we will take one more question from Joe Cavallaro. Joe, go ahead, please.
Sure. Great talk. You mentioned that in your other topics, you're looking at edge computing type applications. I guess my question was that to explore some of the like local sensing, sensor processing, machine learning versus communication trade-offs to sort of study energy issues, energy trade-offs? It
was primarily to look at what you just said, machine learning versus communication trade-offs. Now, in all of these UAVs, what we have done is I have mounted an NVIDIA TX2 board underneath, and it has, I won't say the most capable GPU, but still a reasonable GPU where you can even do some light training on. So what we were trying to do in that paper was to say that, look, if you have a machine learning task to execute, would you send over the raw data over these multiple UAV chains to one that has more free compute resources, but thereby incur a communication cost, and also by way of this an energy cost, versus um, uh, moving some of the other UAVs down closer to the source of where the data is being generated, and thereby reduce the per hop data forwarding needs and compute and execute the tasks on site. So we were basically trying to move the edge closer to the source, and we can do that because these are now UAVs.
Okay, interesting.
Okay, excellent. I think we had a good set of questions. We're a little bit over time, so we'll unfortunately have to kind of call it an end here. But wanted to again take this opportunity to thank Kaushik for great, exciting talk. Lots of fantastic work, very relevant to things which are going on, and also all the audience members for attending and asking a great set of questions too. So thank you so much. Thank you, Kaushik, and thank you all.
Always a pleasure. Thank you again. Bye-bye.
Absolutely. Yeah. Thank you. Bye.